At any rate, let's now return to our main theme of mathematical induction and try to summarize what's happened so far. We are working with a certain conjecture, let's call it. The conjecture is that the limit of a sum is the sum of the limits. We know that the conjecture was true for 2 terms. We proved that once it was true for 2 terms, it was true for 3 terms. We then proved that if it was true for 3 terms, it was true for 4 terms. And now if we have any imagination at all, we might become suspicious and say, you know, I think if it's true in general for n terms, it's going to be true for n plus 1 terms. And that brings us to our next stage in our mathematical induction. Namely, suppose the limit of a sum is equal to the sum of the limits in the case that there are n terms in our sum. What can we conclude about the limit of a sum in the case of n plus 1 terms? And without going through the proof here, we'll do these things in our supplementary notes, in our learning exercises, but here I just want to focus our attention on what the main theme is. What we say is, look at, since we can add without worrying about voice inflection, why don't we throw in a pair of braces here, thus reducing our problem to the limit of a sum when we are adding but 2 functions. Use the theorem there, and now, given the limit of the sum of n functions, we know that that's the limit of the sum, and now it appears that the truth for n is going to imply the truth for n plus 1. Now, of course, there may be other problems that work structurally this way other than the limit of a sum equals the sum of the limits. So let's generalize that result. And the generalization is what is known as mathematical induction. What mathematical induction says is this. Let's suppose we have a conjecture. Now, how we get the conjecture is something we'll talk about in a while. But let's suppose we have the conjecture. Well, to try to show that the conjecture is true all the time, we had better be sure it's true at least sometimes. So we say, okay, let's show that the conjecture is true for n equals 1. That's just a simple verification. We show that it's true for n equals 1. Then we say, okay, next, prove that the truth for n equals k implies the truth for n equals k plus 1. In other words, we're not saying that it's true for k. All we're saying is that if it's true for k, the truth for n equals k implies the truth for n equals k plus 1. Then if that's true, our conjecture is true for all whole numbers. Why is that? Well, let's take a look informally here. We know, let's suppose that both of these conditions are obeyed. We know the conjecture is true when n equals 1. Now, take k to be 1. Since it's true for 1, this part tells us it's going to be true for 1 more than 1, which is 2. Now that the conjecture is true for 2, this says what? It's going to be true for 3. And knowing that it's true for 3, this will say it's true for 4. And now I'll loosely use the word etc. and come back and reinforce that as we go along.